All right, today's lecture, we're going to look at something called PES Diagrams, which stands for photoelectron spectroscopy, which is up at the top. Now, we've done a spectroscopy type way earlier in the year, which is called mass spectroscopy. In mass spectroscopy, what we do is we'll get a graph generated, and that's where we send a sample of an element through a machine that separates the element sample in its individual isotopes. And you'll get bumps and peaks, and each bump is the type of isotope weight that element has. And off to the side here, it tells us the percent abundancy. Okay, so down below, let's say this is 30, and this is 32, and this is 33. The peak that is higher in mass spectroscopy is the isotope that is the most abundant. Of all these isotopes, when we add them all together, let's say this is like 20%, and this is 40%, and this is, let's do this, let's say 35%, and this is 45%. The percent abundances should add up to 100, which would be out of every 100 particles, 35 of them have a mass of 30. So down here would be the atomic mass in AMU. So these would be the individual weights of the isotopes, and then the percentages of each of those isotopes. We can use that information then to go ahead and do a mass, an isotope problem to determine the average atomic mass, which whenever we look up an element symbol, the top number is the atomic number, but the number below is the atomic mass. So we can utilize these numbers to calculate the average weight of the isotope, and that is the number that is on the bottom of all elements on the periodic table. So don't confuse a mass spectroscopy graph from a PES diagram. Okay? So what is a PES diagram? A PES diagram, as this paragraph explains, talks about, in essence, each of these peaks now is actually the amount of energy that a specific energy amount, which corresponds to a specific frequency of energy, that only that element will absorb to cause it to emit electrons. What each of these peaks really is then is the average energy, in essence ionization energy, for us to be able to remove the electrons in that orbital. So each of these peaks is an orbital that we are pulling electrons from. So if we're pulling electrons from the 2s orbital and then the 2p or 3s, no matter what the orbital is, each of these peaks corresponds to one of these orbitals. So the x value is the amount of energy it takes, average amount, because all these orbitals have at least 2 electrons in them. Each peak corresponds to the average amount of energy to pull that electron. Now, the amount of energy it takes to pull, let's say one of the peaks corresponds to 2s. There are 2 electrons in the 2s orbital. That peak, we look at how much energy it takes to remove the first electron and the second, and then they average them together. So that peak is the average of the 2 ionization energies to pull from the same orbital. So the number of peaks tells us the number of orbitals that that element has in its ground state. So in this diagram here, we have 2 peaks, which tells me that we are going to pull from 2 orbitals. Now, lithium, as we know, if I were to ask you to do the electron configuration of lithium, first thing you do in any electron configuration, you must figure out how many electrons it has. Lithium has got 3 electrons when it is an atom. Not an ion, but an atom. And if I do the electron configuration of lithium, it's 1s2, 2s1. Okay? The height of the peak, called signal intensity. Now, while it's signal intensity, this really implies or means the number of electrons that are in that orbital. How many electrons was removed from that orbital? Okay. One last thing that's very important that you'll notice. Typically in x-axis, we will usually start from 0 and get bigger as we go to the right. That's not the case here. Actually, in PES diagrams, the largest energy is furthest left, and the energies get smaller as we go further and further out, and we go further to the right. Why have they done that? They've done that so that the peaks, the order of the peaks, follow the order in electron configurations. So the order, again, if we go back a couple of lectures ago, the first orbital is 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p, and so on and so forth. These peaks, because we have the highest energy first, the first peak always corresponds to 1s, then 2s, then 2p. They go in perfect order across from left to right. Because of this, since we know the s orbital takes up to 2 electrons, we know the height of this implies 2 electrons. So the first peak allows us to determine the scaling of the y-axis. How many lines up does that mean for an electron? You just can't assume that each line up is 1 electron. So in this diagram, every 2 lines up is 1 electron. The next 2 lines up is 2 electrons. So the height of the y, that first orbital, that 1s orbital, that will tell us the number of electrons and give me the y scaling. From there, I have all the information I need. I know the first orbital is 1s, then is 2s, and by knowing the height of the 1s, if there's a second peak, the first peak, the 1s, has had to have been full, and therefore I know the number of electrons in each of the orbitals going out forward. Okay? So, from that, the first peak corresponds to 1s, 2, and the second peak, you'll notice, is half as high, so instead of being 2 electrons in it, there's only 1 electron in it. The PES diagram gives me the electron configuration of 1s2, 2s1, which matches what we already know. So oftentimes, they might not tell you what the element is. Your job is to figure out what element it is, and you can do that by understanding what each of those peaks means. So it's really not difficult. You just have to know what that means. And again, first thing to check for, make sure the largest x value is furthest left. If that is the case, the first peak that you hit going right is 1s, 2s, all the way out. And then use the height of the 1s peak to be able to determine your y scaling. Once you have that, you can use this. It literally becomes a graph that we can get the electron configuration from. That's all it is. So let's turn the page. All right, before I get to this last problem, let's say we had a diagram electron configuration. Oops, my bad. Okay, which element is this? All right, and let's say down here we've got the largest energy, and down here we've got 0. And over here this would be the signal height. As I said, if the largest x value is left and it gets smaller as we go to the right, that tells me this is the 1s peak, 2s, 2p, 3s, 3p, 4s. And if this stands for 2, because we know 2 electrons fill the 1s, if I do my scaling somewhat right, I know I'm just kind of eyeballing it, okay, I can now figure out that the electron configuration of this element is 1s2, 2s2, 2p6, 3s2, 3p6, and the 4s peak is about half as high as the 3s, so instead of being full, there's probably only 1 electron in there. So that would be the configuration of that element. And which element is that? 4s1. I believe that this is the element potassium, because if I add up the superscripts, 2, 4, 10, 12, 18, 19, this element has 19 electrons. If it's an atom, that means it has 19 protons. Atoms have equal protons and negative electrons, and that is the element potassium. So this would be the PS of potassium. So one thing to look at would be identifying what the element is, and then maybe they ask a question off of it. The second type of question that they've asked since the redesign is this one right here. They show both of these PES diagrams. One is for carbon and one is for nitrogen. Each of these peaks they're talking about is the 1s. Now, if I look at it, for carbon, the binding energy, or the energy it takes to remove both electrons, is a value that looks like it's around 300 electron volts. Nitrogen is around 400 electron volts. We're pulling from the same orbital. Why does it take more energy to pull an electron from nitrogen than it is carbon? And actually the exact values, I wasn't even looking, are down here. So for carbon, to pull the electron is 286 electron volts. For nitrogen, it's that. If they're pulling from the same orbital, why wouldn't it be the same binding energy? Why would it take more energy to remove the electron in nitrogen's 1s than carbon's? And the why is nuclear charge. Nitrogen has got 7 protons in the nucleus. Carbon only has 6. And because of that, nitrogen has got a greater nuclear charge, and this then causes a greater coulombic attraction, or a greater pull from the nucleus on the electrons in the 1s, and therefore if there's a greater attraction of the electrons to the nucleus, it's going to take more energy to ionize the electrons from that orbital. So that's another type of question they might ask, where they're pulling from the same orbital, but the amount of energy it takes to pull from is different. And then that, again, we're looking at, in essence, a concept ionization energy, which we talked about yesterday. So those are the two types of questions. Really, all the PSC diagram does for us is it gives us a chance to create a graph and then take the information from the graph to write an electron configuration, and then we treat it just like we did yesterday. Just adds in one extra step to the problem. But if you know what the PSD diagram is, what it gives us, then again, it's a fairly easy question. Now, I don't have a homework set for this stuff. What I'm going to do instead now is on Canvas, I am going to upload the atomic structure quiz that I gave last year. I'm going to upload it on Canvas, and I'd like you to go ahead and take that quiz. In that quiz, there is a lot of PS diagram questions. I'll then also upload the answer key, and if anybody has questions on any of those, I'll be glad to take them over. I'm looking at maybe next week of spring break. I plan on uploading a lot more information on Lewis structures. I don't expect you to do it, but if you're bored and you want to do something, please do. But I plan on the week to follow. I don't anticipate us probably coming back to school yet. But that week I might even have an online chat session, and then people can start bringing me questions, and some of those questions may come from some of the homework sets that I've assigned over this last week, or even this atomic structure quiz. So please take a look at that quiz. Try to do it. It's good practice going into the national exam, which is going to be in about a month and a half from now. All right. So good luck. If you have any questions, again, send me an email or send me a notification through Canvas. I'll be glad to get back to you as quickly as I can. Have a great day.